Okay, this is a review of Chapter 3. Now we led into Chapter 3 from Chapter 2, talking about water being a polar molecule, forming these hydrogen bonds, which are attractions between water molecules. Now, water is essential for life on Earth. Most of the Earth is covered with water. Most of an organism's mass is water. And all of the life's biochemical processes happen in water. So, everything you know about water, and everything about water that allows for life to exist, owes itself to these hydrogen bonds which attract them together. Now, under Roman number 1, it talks about effects of water's polarity. Now, if you look on page 47, it shows you a water molecule that is forming up to 4 hydrogen bonds with its neighboring molecules. Now, depending upon the state of the water, they won't form all 4 at the same time. They can form and break as they're doing it. Now, effect of water's polarity. Water is a polar molecule. It's a small molecule that behaves like a big one. It allows for cohesion of water. Okay? Cohesion means the molecules tend to stay close to each other. So, being closer, it will allow the water to remain a liquid despite its small size. See, methane is nonpolar. There are no attractions of methane molecules. Methane is a gas. If it weren't for the bonds that force molecules to become closer, water would also be a gas. And we wouldn't be here to talk about it. So with a liquid, the molecules are fairly close together. They're rolling around in a fluid-like way. In a solid, they're close, but they're rather limited in their movement. But in a gas, they're moving at random. Keep that in mind as we talk about this. So water has cohesion, water has surface tension. Page 48 shows a little water strider standing on the surface tension of water. The water molecules at the surface tend to align, causing surface tension. Another property of water that owes itself to this is that water moderates temperature. Now, it takes a lot of heat to raise the temperature of water, because to raise the temperature of water, you're going to make the molecules move faster and move harder, and you got to overcome the forces that are keeping them from doing that. That takes energy. Now, water has what's called a high specific heat. The specific heat of water is 1 calorie per gram per degree Celsius. It takes 1 calorie of heat to raise 1 gram of water by 1 Celsius degree. Now that's pretty high compared to other substances. So it takes a lot of heat to raise the temperature of water. And because of that, water retains heat well. So it takes a while for water to cool off once it has absorbed some heat. Excuse me. Now that's good for us because we're mostly water and we want to maintain a constant body temperature. Now, if water has a high specific heat, it also has a high heat of vaporization. To vaporize the water, you have to convert all of the liquid water to a gas state. To that, you've got to overcome all of the hydrogen bonds at the same time. That takes a lot of heat to do that. So, it takes, if it takes 1 calorie of heat to raise 1 gram of water from 99 degrees Celsius to 100 degrees Celsius, which is the boiling point of water, it will take an additional 540 calories to vaporize that 1 gram. So if you're boiling water, you have a thermometer in the water. Once it starts to boil, the water's not getting any hotter. All the extra heat is going into vaporization. Now because this happens, and because water evaporates anyway, water removes heat when it evaporates. That's known as evaporative cooling. That's why we sweat. We sweat to use evaporative cooling to get rid of heat. Another property of water is that ice floats. Ice floats because ice is less dense than liquid water. This is very unusual. Most substances will sink as solids within their liquids, but ice is the opposite. Now, the reason for this, again, hydrogen bonding. If you look carefully on page 50, as you cool water down, the molecules will slow down and get closer together. So water will become more dense as you cool it down, up to about 4 degrees Celsius. Then when it gets cooler than that, they become less dense. And the reason why is because they're slowing down so much that they'll start to form more stable hydrogen bonds at the same time. So if every molecule of water is forming 4 bonds with every other water molecule, the geometry of the bond angles forces the molecules to spread apart because they can only be so close together and form all of the bonds at the same time. Ice expands and it floats. The reason why that's good for us and for the planet is that if ice sank, then all of the oceans would be permanently frozen from a few feet down, and that's no good. So those are properties of water. Another property is that water is a versatile solvent. Solvent means it can dissolve things. Salts dissolve well in water. Other polar molecules like amino acids and sugars, which we use as nutrients, dissolve in water. But some things can't dissolve in water, like oil. Okay? Things that can dissolve are hydrophilic. Things that don't dissolve are hydrophobic. Okay? So that's important for life as well. Now, on Roman numeral 3, we have on page 53 acids, bases, and pH. Now, the text here explains acids, bases, and pH, especially on that drawing of the water molecules on page 52. In small amounts in pure water, some of the water molecules dissociate into the hydronium ion and the hydroxide ion, and then they spontaneously form back again in small amounts. So in a neutral solution, that is pure water, you're going to have the exact same amount of the hydrogen ions as you do the hydroxide ions, and that's known as a neutral pH. And the actual concentration is 10 to the minus 7, and that's where the 7 comes from on the pH scale. It's the negative exponent of the hydronium or hydrogen ion concentration. That's what pH is, and that's where the numbers come from. Now, things you need to know. On the pH scale, it ranges from 0 to 14. 7 is neutral. 0 to just below 7, acidic. Just above 7 to 14, basic or alkaline. And with an acid donates or increases the hydrogen ion concentration, like hydrochloric acid would. A base does the opposite. It lowers the hydrogen ion concentration, like sodium hydroxide would. These examples are in your text on page 53. Other things to know about the pH scale, it is a logarithmic scale. It is not a linear scale. Each number on the scale is a factor of 10. So pH of 2 is not twice as acidic as pH of 4. It is 100 times as acidic. So each notch on the scale is a factor of 10. 10, 100, 1,000, and so on. And that mostly covers this chapter, but keep in mind we have to have pH balance in our body tissues. We have to have what are called buffers. Buffers are chemical systems that resist changes in pH. So that's part of pH homeostasis in the body. Again, study your notes and use the review session to kind of help you with it.